Okay, I write down it again so that it will be easier for us to check later on. Lyapunov functions if v dot is less than 0, so the system is unstable. If v dot is equal to 0, the system is marginally stable. If v dot is greater than 0, so the system is terbalik. If v dot is less than 0, so the system is stable. If v dot is equal to 0, the system is marginally stable. If v dot is greater than 0, so the system is unstable. Okay. Okay, example number 2 for Lyapunov. Let's say I have one equation. 2x double dot minus x dot plus x 1 minus x squared equal to 0. So then you use state space. So we get state equation. So you convert to state equation. So x1 dot equal to x2. x2 dot equal to x2 over 2 minus x1 over 4 plus x1 power of 3 over 4. Then the system gives you the Lyapunov equation for this particular systems. V equal to s1 squared plus 4x2 squared minus x1 over 2 power of 4. So normally in the questions you will be given number 1 the differential equations for the systems, and then number 2 you will be given the Lyapunov function for that particular systems. So what you have to do first, you have to convert the differential equation to the state space equation. Okay, and then by using the Lyapunov functions given, you have to find v dot in order to determine the stability of the system. Okay, differential equations, convert to state space form, and then Lyapunov function will be given. So you have to use the Lyapunov function to get v dot in order to determine the stability of the system. Okay, so again, v equal to x1 squared plus 4 x2 squared minus x1 power of 4 over 2. Okay, we will use partial derivative. Okay, so it is maths. I think you heard before about this. And then our Lyapunov function, it have two x functions, v x1 and x2. So we find the v dot on x2, x1 first. Okay. So here is 2 x1 dot plus 0 from here minus 4 x1 power of 3 over 2 x1 dot. So you will get 2 x1 dot minus 2 x1 power of 3 x1 dot. Okay, so the second one, so derivations of v on x2. So v dot function of x1 x2. Now we derive derivative of v on x2 equal to, so here is 0 plus, here is 8x2 and here is 8x2 x2 dot minus, here is 0. So now we sum up everything. Okay. Therefore, derivative of v x1 x2 is equal to 2 x1 dot minus 2 x1 power of 3 x1 dot plus 8 x2 dot. So here is your v dot equation. V dot equations, okay, for the system. And we do have the equation for x1 dot and x2 dot from the questions. It have given by these equations. No, you have changed the differential equation to state space form. Okay, so here is 1 and this equation is 2 for x1 dot and x2 dot. Now we will substitute the equation in v dot. Okay, so we write it again. v1 dot is equal to x2, while x2 dot is equal to x2 over 2 minus x1 over 4 plus x1 power of 3 over 4. Therefore, v dot x1 x2 is equal to 2 x1 x2, okay, so from here, minus 2 x1 3 power of 3 x1 dot. So x1 dot is equal to x2 plus 8 x2 dot, and x2 dot is equal to x2 over 2 minus x1 over 4 plus x1 power of 3 over 4. So from here, okay, we expand the equation. So you will get, okay, sebelum tu, so here is x1 dot, here is x2 dot. Okay, now we expand the equation. You will get 2 x1 x2 from here minus 2 s1 cube x2 from here, okay, plus 4x2 squared, okay, so it's from here, here and here, okay, minus 2x1 x2 from here and here, plus 2 x1 power of 3 x2. So you can cancel 2x1 x2 minus 2x1 x2, okay, and then negative 2x1 power of 3 x2 plus 2x1 power of 3 x2 cancels, then you get 4x2 squared. So from here, if x2 greater than 0 or x2 is equal to positive, so you substitute the equation, v dot equal to 4 positive, so v dot is greater than 0. If x2 less than 0 or x2 is equal to negative value, so v dot equal to 4 times negative value squared. So you still get v dot greater than 0. So from here you can conclude that for these particular systems, okay, where v dot x1 x2 equal to 4 x2 squared, even you use x2 greater than 0 or x2 less than 0, you still get v dot greater than 0. So it means that any value of x2, the system is remain unstable. So two examples for Lyapunov. Then next is linearizations. Okay, the last part for this chapter, linearization. Okay, linearization. Okay, let's say you have one equation. So 2 double dot minus x dot plus x 1 minus x2 equal to 0. So now the system is linear or non-linear. So there are two characteristics of non-linear system. First, the higher order is greater than 1, and then or is either 1, okay, it's not n, it's or it has a dependent equation or dependent functions. Okay, so from this case, it has a higher order is greater than 1, so the system is non-linear system. But we have one option to convert the system to linear system by using linearization. Okay, let's say you have one graph. that represent one non-linear system. Okay, so it curve graph. Okay, so you have a phase plan x1 dot equal to x2. This one is x1. Okay, so here is your graph. Okay, so we have one option to convert it to linear system. Okay, by take just a few samples of data from the system that represent the system, something like that, and we call it as a linearizations approximation. Okay, from here, okay, from nonlinear system we'll make some approximations and we get this system. Because from the nonlinear graph you can see that there are one part in this graph that look like a linear function, so we just ignore other part and we just use this part to represent or to approximate the linear functions. Okay, so from here, from nonlinear graph, nonlinear system, nonlinear functions to linear graph, linear system, linear function, we use Taylor series expansion. Okay, Taylor series expansion. So what is the Taylor series? Okay, the Taylor series is fx equal to fx naught plus d over dx for fx, where x equal to x dot times x minus x dot. Okay, so it seems complicated. So now we see the one example, okay, for explanations. Okay, new page. Let's say you have one in inverted pendulum systems. Okay. Here is the data value. And linearization only can be done at the system rest condition or at equilibrium point. Okay, so based on these systems, where is the rest condition? Okay, so if you put your inverted pendulum here, the system will keep moving, okay, left and to the left and right. If you put your inverted pendulum here, so the system is not moving, so it means that instead at these positions the system is at rest condition. So at the rest condition, the theta value is equal to 0 and we name it as theta naught. Okay, And the input t naught also equal to 0. Because if you give any input to the inverted pendulum, the system will moving. So now the system is at the rest condition. So input is equal to 0. So this what we call at the rest condition. Okay, so you do the modelings. Okay, you do the modelings. And then you get the equation that represent the system is T equal to mgl sine theta. So the system is nonlinear or linear? The system is nonlinear. Why? Because if you draw the sine theta, okay, you get the curve graph. So the curve graph is nonlinear. Right? So now we use Taylor series to linearize the equations. Okay, so fx equal to fx naught plus d over dx for fx, where x is equal to x naught, multiply with x minus of x minus x naught. Okay, so this is the Taylor series. And from the equation, if you can see, there are two functions, x naught, x naught, x naught. Okay, so you have to determine what is x from the equations. So I write it again. T equal to m g l sine theta. Okay, so what is x from these equations, where x is changed throughout time? Okay, change throughout time, x. So m is constant, m is mass, g is constant, g is gravity force, l is constant, l is length of the inverted pendulum. So here the only function or value is changed is theta. Therefore, x is equal to theta. The only function that change throughout time. And fx is equal to t theta. Okay, so we write it again in the form of t and theta. So from here, we know that x equal to 0, x equal to theta, and fx equal to t theta. So t theta is equal to t theta naught plus d over d theta for t theta, where theta equal to theta naught multiply with theta minus with theta naught. And we know at the rest conditions, when theta naught is equal to 0, okay, mana rest condition tadi? Okay, here. Rest condition, when theta naught equal to 0, t naught also equal to 0. So this is the rest condition. So we substitute in the equations, and you will get 0 plus. So you differentiate the equation on theta. Okay, from here. So you will get mgl cos theta and you have to substitute theta equal to theta naught, which is 0. Okay, alamak. Okay, tu pandang balik. Okay. So, okay, we start again. So, theta 0 is equal to 0 rest condition plus t theta, differentiate t theta. Okay. So, mgl cos theta and replace by theta equal to 0 multiply with theta minus 0. Okay, because theta naught is equal to 0 from here. Okay, so we substitute the equation. mgl cos 0 times with theta okay, where cos 0 is equal to 1 is cos 0 is equal to 1. So therefore t theta is equal to mgl 1 times theta. So it's get we mgl theta. Okay, so now we have two conditions. One, before we linearize nonlinear, t theta equal to mgl sine theta. And then by using Taylor series expansion, we did the linearization. Okay, and then we get the linear functions. T theta equal to mgl theta. So the nonlinear function in the nonlinear system have been removed and be replaced with the linear function theta. And this function only valid at theta not equal to 0 and t not equal to 0 when the system is at the rest conditions. When system is at rest condition. So if I can summarize the linearizations part, okay. So linearization, okay. So we convert nonlinear functions or system to linear systems or functions by using Taylor series expansions. Taylor series expansions. Okay, so the equations fx equal to fx naught plus d over dx for fx when x equal to x naught, and then multiply with x minus x naught. Okay, then you have to find the value of x naught and fx naught. What is the value? So the conditions or the value of x naught or fx naught you can determine when the system is at rest conditions, or the conditions or coordinate when your system at equilibrium point. Okay, so if we draw the graph, so here is the non-linear graph. Okay, something like this. Okay, so we linearize the systems by using Taylor series expansions, and we get these functions. Okay, so obviously from here we extract from the non-linear systems the function, or approximate the equations, or extracts data from the non-linear functions or graph, and linearize it, and we take part of it that represent the linear functions for the system. Okay, so I think that's all for chapter non-linear system. So I already cover equilibrium point, linearizations for today's video lecture, and then a few examples on Lyapunov functions or theorems. Okay, so that's all guys. Thank you and have a nice day. Bye.